Hello everyone. In this video, we'll be discussing the fourth problem of our week 1 problem set. So the fourth problem says that if you have a function which is twice differentiable and your double derivative is continuous on an open interval in R, then you have to prove that limit h tends to 0 f of x plus h minus 2fx plus f of x minus h by h square. This limit goes to f double dash x, and this is nothing but the double derivative formula of a function. So let's see how we can do this. So what do we know about f double dash x? That is nothing but limit h tends to 0 f dash x plus h minus f dash x by h. Right. Now I claim that this is also equals to limit h tends to 0 f dash x minus f dash x minus h by h. Now how do I claim that? So let's take minus of h to be k. Then what we have is f double dash x. We know this. So let's replace h by minus k there. So minus k tends to 0 and f double dash x plus minus k minus f dash x by minus k. So this becomes limit. Now we are multiplying with the minus sign both above in both the numerator and the denominator. So this becomes k in the denominator, and the numerator becomes f dash x minus f dash x minus k. So you see that if we just replace k by h, so we are getting this, what we claimed. So this is going to be useful. Let's see how we can use that. So remember, in the problem we had an open interval I where all these operations were happening. So let the open interval be I. Suppose P is a point in the interval I, and our function f is a function from I to the set of all real numbers. And now suppose f double dash p exists, then we have to prove that f double dash p is nothing but limit h tends to 0 f of p plus h plus f of p minus h minus 2f of p by h square. Now if double dash p exists, now what does this mean that it exists? So this implies that there exists a delta greater than 0 such that f dash exists on p minus delta and p plus delta. So basically this means that you have an open interval around p, however small it is, where f dash exists, and f dash is continuous at p. At the point p it's continuous. Now we'll define two functions, a of t, which is nothing but f of p plus t plus f of p minus t minus 2 f of p, and our function a is not, its domain is 0 comma delta to r, and we'll define another function t, which is nothing but t square, and our function b is also going from 0 delta to r. So we have basically taken the numerator to be the function a and the denominator to be the function b, and clearly you can see that both the functions are differentiable. Now let's find out limit t tends to 0 plus a of t by b of t. So if you can see that this is nothing but of the form 0 over 0, so we can apply L'Hopital's rule, and this would be equals to limit t tends to 0 plus a dash t by b dash t. Now, provided that the limit on the RHS exists, so we have this to be equals to limit t tends to 0 plus f dash p plus t minus f dash p minus t by 2t. So this will be equals to limit t tends to 0 plus. Now I'll add one f dash p and subtract one f dash p in the numerator, and I will just basically divide it into two groups. That will become f dash p plus t minus f dash p by t plus half of f dash p minus f dash p minus t by t. So now you see that we have already proved that f double dash x has this two forms, and we have those two forms here, and so we can write them as half f double dash x plus half f double dash x, and this is nothing but f double dash x. So now we have proved that f double dash p is equals to limit h tends to 0 plus f of p plus h plus f of p minus h minus 2f of p by h square. And similarly, for the case h tends to 0 minus, we can prove it similarly, and finally we will be having our double derivative formula for any arbitrary point p on the open interval I. Thank you.